Hey, pre-calculus folks. So last week we used limit notation and everything like finding limits to find the instantaneous rate of change of a function at a particular point. So this week we are going to take it one step further, jumping to 12.4 in your book, and talk about derivatives. So derivatives and instantaneous rate of change of a function are actually the same thing. When we calculate instantaneous rate of change, usually we're calculating it for one particular point. When you calculate a derivative, you can calculate that for like all of the points along a function, as long as it's differentiable. But you can also, calculate it for one particular point. And you can also do it with the same limit definition that we've been using for finding instantaneous rate of change. But there's some more notation for us when we talk about derivatives, because if I start with a function, f of x, and I take the derivative of that function using my limits and everything, the new function that I get, f prime of x is what we call it, is the function of the derivative of this function. So it's the, if I plug in, any value for x, I should get the instantaneous rate of change of this function at that x value. So I'll get the derivative or the instantaneous rate of change at any x value by plugging in a value for x here. So we can do this using the same limit definition of an instantaneous rate of change or derivative that we've been using. So let's say we have f of x equals x squared minus 2x plus 3. So if I'm going to take if I wanted to find the instantaneous rate of change or the derivative at just one point, remember we had that definition. It was the limit as h goes to 0 of f of x plus h minus f of x over h. So if I wanted to find it at just a particular x value, I would plug in my x value here and then, solve through this limit. If I want to find the derivative for the whole function, if I want to find my new derivative function, I can just plug in x plus h to this and then plug in the function here and solve the limit the exact same way. So let's do that. So x plus h is going to go in anywhere there's an x here. So we're going to have x plus h squared minus 2 times x plus h plus 3. So that's my f of x plus h that I'm plugging in. And when we do this, we want to make sure that we, multiply this out. So we actually get x plus h parentheses squared is x squared plus 2xh plus h squared. And then I want to also distribute the negative 2 through. So we have negative 2x minus 2h. And then plus 3 is also hanging out there. So that's my f of x plus h part of this. And then we're going to run out of room here. And then f of x, so it's minus f of x. And remember, it's minus the entire function. So if it helps, you can go minus parentheses x squared minus 2x plus 3, so that you remember to distribute the negative to all three pieces there. And then it's all over h, and it's the limit as h goes to 0. Okay, so now I'm going to go ahead and distribute the negative through here. So we end up with minus x squared plus 2x minus 3. Now we got to figure out which things cancel here. So we've got a positive x squared and we have a negative x squared. So those can cancel right away. We have a negative 3 and a positive 3, so those can cancel. And we have a plus 2x and a minus 2x, so those can also cancel. So let's rewrite this with what we're left with. We've got the limit as h goes to 0. We have 2xh we have h squared and minus 2h. And it's all over h. And now, hopefully we've noticed that we have an h in each of these terms. So I can factor out an h and cancel it with the h on the bottom, or you can just think each of these that has an h in them, we're going to get rid of one of the h's. So this is just going to become h, not h squared. So now we have limit as h goes to 0 of 2x plus h minus 2, and the h on the bottom is gone. So now we don't have that dividing by 0 problem anymore. So now I can let h go to 0, and it turns out what we are left with over here is just 2x minus 2. Okay, so what that tells me is that my derivative of x squared minus 2x plus 3 is 2x minus 2. So if that's f of x, f prime of x is 2x minus 2. And then if I wanted to find the value of the derivative at any particular x value, like let's say I wanted to find the derivative when x is 1.2. So then I would just plug into f prime 1.2. So 2 times 1.2 minus 2, which would be 2.4 minus 2, which would be 0.4. So that would be my derivative for this function at x equals 1.2, my instantaneous rate of change of this function, the slope of the tangent line of this function. Those are all talking about the same thing. So the slope, if I had a tangent line to the function at 1.2, the slope of that line would be 0.4. And I could do this to find any value of the instantaneous rate of change or the slope of the tangent line of the function by plugging in any x value here. So that's kind of cool. All right, so that is how you calculate a derivative using limits. In calculus, you'll learn all kinds of different ways you can calculate derivatives that's faster than taking a limit every single time. But that limit definition works for us right now. Hopefully this was helpful. If you have any questions, feel free to comment, come to office hours, or send me an email. Have a good one.